Japan, and we input those kind of data, solar radiation or temperature, humidity, wind, and so on. Through this input data, cropped yield model. Through cropped yield model, we can get some estimations factors. In this case, yield at the bottom chart, the dimension is tons per hectare. So estimation value is made by crop yield model shows 2.04 tons per hectare in this area. And institute data, actual measurement of the crop yield is 2.46. So it's simply to multiply to this average and yield, we can get the information of production in this area. So estimation is 33 tons, and institute is about 40 tons. The accuracy is, you can see, 81% or more. This is not enough to actual activities. We will make more effort to increase up to 90%. This is our future issues. Okay. Thank you for your attention and session. So I will introduce to Dr. Matsumo.
I'd like to remind everybody, please write your questions, and the IAF staff is walking around. They have sheets, so we can bring them up front here. Thank you.
Good morning, everyone. In this last talk of this morning, I'll try to provoke your reaction on a statement which is included in this title. In the sense that, as we have seen, some measurements from space can capture important terms. I will even argue can capture all terms of the water balance over the global land surface. But the question is that global information the same thing that we need for actual water management, so to address the societal relevance that had been stated also in the introduction by Jim Graff. Now, if you look at this diagram, you see on your left a chart that you may have seen in different versions endless times, which describes the water cycle. That is the phase transformation, the physical process that govern the water availability over land. On your right, you see a different diagram with numbers, which shows the volumes which are actually controlled by what we do with our water management systems. When we decide where to allocate water, when to allocate water, when to release water from reservoirs. And so these are very large amounts of water. In many parts of the world, the controlled part of the terrestrial water cycle is largely overrides the physical processes. And so information, including data from space, if they are to be relevant for actual water management, have to be consistent with the spatial and temporal scales at which the decision that determine those flows, those numbers, we are talking about thousands of cubic kilometers of water per year, at which those volumes are, so to say, decided upon. And now, if you look at what people is doing today with space data in relation with hydrology and water management, you would end up, at least that's my interpretation of what we are saying. And you see first on the top left of this diagram, you see a multitude of satellite platforms Each satellite is most likely the node is carrying multiple sensors. So you end up with a very large family of instruments in space, many of those capturing similar signals and which are being used to derive similar biophysical variables, including similar hydrological variables. And then this data take, so to say, two different ways. On the one hand, you see the chart on the top right of the diagram. High-resolution data are being increasingly used worldwide to develop, provide water management support services like farmer advisors on irrigation. And what you notice in the implementation of these services is that the focus is on water use regardless of water availability. They would say that doesn't make much sense, but that's what it is. It's a commercial, these are services commercially set up, providing information on how much water is needed where today and how we are using water there. On the one hand, you see the central chart, which describes, or is supposed to describe, how global data from satellites are used for global analysis of water resources and hydrology. And now my argument is that we need something in between the global analysis of the terrestrial water cycle and the advisories on water use, and that's the box about river basin models, because there is where the actual decisions on water use, water allocation, and water management are taken, and that's what determines water availability at the local scales, where the other high-resolution data about water use are being delivered, provided in an increasingly effective and timely way. So once that loop is complete, then we will end up in a situation where global models are much better linked with the actual water use, and so the societal aspects related to water availability, agricultural food production, and so on. And in my conclusion, I will briefly get back to these statements. Now, the European Space Agency is responding to these challenges besides developing new sensors and new platforms, is responding to very specific ways. On the one hand, over the last few years, has launched the Climate Change Initiative, which specifically is actually specifically doing the development of extended time series of essential climate variables as defined by the Global Climate Observing System. And these are, in principle, 30 years time series of consistent data on biophysical, geophysical variables extracted from sensors that have evolved over time. The microwave radiometers of 35 years ago are not the microwave radiometers we are using today, but they can be used to derive similar variables. That's the effort which is taking place under the Climate Change Initiative, developing at the moment 14 different major variables. On the other hand, the European Space Agency in Africa and Asia has implemented programs, the Tiger program in Africa and the Dragon program in Asia, where, so to say, the data collected not only by the ESA but also by partner countries and partner agencies are being used in support of understanding of water science and application. And then you may even see that there is a difference. In China, the emphasis is on advanced water science on a really equal level with the rapidly developing high-level system of research and education in China. In Africa, there is a balance between development of applications and capacity building. Now, I know you cannot read this diagram, at least you cannot read the text in the boxes, and what this is meant to summarize the flow of data from say, sensors in space to the actual use for monitoring and early warning on drought and floods. And so the circles on the upper part of the diagram are different data streams, and 5 of those circles describe data streams from going from left to right on biophysical properties at the land surface, the amount of vegetation, the photosynthetic activity of vegetation, etc. And the second circle is about monitoring radiative and convective fluxes at the atmosphere interface. And then we go to soil moisture, precipitation, and snow and ice on the last circle on your right. All this data go into this. I will show in a minute actual results done with the system built on this logic. But the logic applies to many other efforts and projects. And so these streams of data go into hydrological models and land atmosphere model, where the hydrological model is the thing that delivers assessment and monitoring of water resources, and the land atmosphere model describes how the land surface condition determine, and it is particularly relevant in Asia, determine large-scale convective processes and intense precipitation events elsewhere, that is away from the region where we are observing patterns of dryness and wetness and the development of vegetation. At the bottom of the diagram, you see 2 cases of actual use of time series of data which come out of this combination of satellite data and models for drought and flood monitoring and early warning, where the name of the game is to have time series reliable to the point that you can timely detect anomalies and use those in developing anomalies as an early warning signal to take action and do something with the water management, allocate water where that may be needed. Now then I could entertain you for an hour, explain what is behind this picture. This is like the time series and Fourier analysis and power spectra and a combination of amplitudes, and basically it says how much vegetation is at some place, how it is developing in terms of intra-annual variability, and especially when is the timing of anomalies in vegetation development. Now, if you do this continuously over a number of years, you have an excellent tool to detect where, when, and how serious anomalies in agricultural food production are developing, and so again, take timely action. Now, I promised to show some results. Now, this is a result of the application of the system I was describing a couple of minutes ago to the region, including the Tibetan Plateau, that's the area that you see within that red line, and most important, to the headwaters of the rivers which are coming down, streaming down from the plateau, and rivers that are supplying water to a slightly less than half of mankind in all the countries of East and South Asia. But the point is that the combination of wall-to-wall satellite data on the terrestrial water cycle and modeling tools allows the production of information on fresh water available across political borders. This region is quite sensitive for that reason, so talking about water that is streaming down of the plateau to Pakistan, Bangladesh, India is relevant and provide information that is not so easy to get by any traditional means. And last point of this short argument is that global air system models are evolving in the direction that the terrestrial water cycle is included at an increasingly high spatial resolution, to the point that real river systems, where you can essentially identify in global models specific elements of a channel system, and so elements where the season of water management are represented in global models, so linking in a much more precisely understandable, usable way the global processes with actual decision of water management at the local scale. And with this, I would like to thank you for your attention.
Excellent, thank you. each and every one of you. This is on. Can you hear me? We have some interesting questions to ask the panel here. There's one I'm going to ask Dr. Wu first, but I'll ask also the two of you if you'd like to comment. To understand impacts of drought on agriculture, it's necessary to get good in situ measurements. Therefore, there must be a collaboration with the non-space sector, people from the Ministry of Agriculture, as an example. Could you explain the situation of collaboration with people from the agriculture sector and challenges you realize, and how you approach that to overcome the challenges?
Yes, thank you. For the answer these specific questions, I'm talking about a little bit of a concept, how satellites information can be used in the agriculture, water cycle policy. We are a satellite generate a lot of plenty of information, which is maybe 10,000 times than the traditional discipline can obtain from the in situ measurement. So the methodology to use satellite information should be different from the traditional principle, traditional methodologies. So that's the one of the concepts. When we are develop crop watches, we are stick to the more sensing informations. Of course, we need to use in situ data to calibrate our models. But those in situ data should be measured to match the pixel information. You cannot say one point measurement from the fields can be used to calibrate our model in pixel size. So this is the difference. So most of in situ data from traditional methods are not capable to calibrate the more sensitive information. We need to develop our own in situ data. So when we are using in situ measurement to calibrate our joint models, global models, or yield models, we around the China, we are select our own in situ plots and make a field measurement and carry out models. The agriculture sectors are users for these informations.
If I may, I would like to add a comment to this, that in there's the projection that we see of climate impact on agricultural production and the assessment, the real-time assessment on impacts of weather variability on crops, I think that we are not taking sufficient account of agricultural biodiversity, in the extreme diversity, in the responsive vulnerability of different cultivars, which is very important, especially for the most important staple crops. Like there are hundreds of varieties of maize, and they have very different vulnerabilities in terms of critical water deficit, temperatures. The same is true for wheat, and in our modest perspective in Europe, also olive and vine are extremely diverse in terms of cultivar-specific response to climate and weather. And this aspect is very difficult to take into account with models, but the same fact that there are no libraries of variety-specific model parameters.
Okay. Thank you. Let me move on to another. Azhar Khan from Pakistan has asked, I'll put this to you, Dr. Homa. The global precipitation data that we've talked about is very important to them and to others out there, and they would like to know if they could get access to that data.
Well, so as I showed in this my chart, the access is free, and please click through your internet network, and
could they access a website that you have and get access to the data that way?
Yes, that's right. Anytime.
And let me ask a follow-up question for all of you, and that is, there's a lot of interest, we're getting a lot of questions from the audience about the crop estimation, growth estimation data that we presented here, all of you have presented, you know, is that modeling and that simulation, can it be shared with others?
Yes. Yes, when we are, the crop watch is divided into two different scenarios. One is for the global and the major producing zones. And in these two scales, we are using most free of charge data, like chip data, global precipitation data. We using power data generated from geostationary satellite data. We use temperature data from satellite data also. And we use this can analyze the environment impact to the crops. And for the major producing zones, we are using high resolution data to estimate biomass, crop index, paradigm ratio. All this information are available in the crop productions. And these can be accessed free of charge, free access from internet. And on the country levels, the software can be deployed in the other countries. We are working together with Pakistan, with Thailand, with Kenya to transfer our technologies.
Well, so data policy of the Earth observation data is very, very important issues. And I know as a United Nations or some international organizations, so-called GEO or CEOs, is now under discussion. And in Japan, basically, Earth observation data is free and can provide any users. But there's one exception, except higher resolution data. So that is the current common understanding of Earth observation data policy, to my understanding. So many issues what discussed today's session, we can provide necessary data by through internet, or to make more precise information, please contact to JAXA to make some agreement. That means some, not only data is enough, some algorithm or some model is necessary to answer so yours.
As far as I know, except the very high resolution information, for example, there are a number of web resources where you can get farm-specific data, and that usually works through a subscription, in theory as a price. In practice, most of these systems are developed with subsidies from government, so again, the restriction is relatively soft. All the other data at larger spatial scales are in general public domain. And in that sense also the effort of the GEO international intergovernmental agreement are really effective in the sense that both satellite data and derived products are increasingly easily and freely accessible worldwide.
So, thank you. We have a few more questions. One is, we have been talking about agencies investing, developing this infrastructure, the spacecraft, and of the model and disseminating. The question really is, how can we involve the commercial and the private sector in these activities?
My second crop watches has been transferred to the China Grain Storage Corporation. So they use this technology to monitor themselves. And they make money. Because once you know the crop production, all these stages, so they can go to the future markets, stock markets, to play.
we from Space Agency, we are very much welcome to come on the private sectors to enter this observation business because they have a private sector have very sophisticated tools and internet, network. So by use of the private sector's such knowledge and network, we will receive more fruitful results by use of assessment data.
And again, I think it's good to make a distinction between high resolution and low resolution global large area coverage data and information. And for example, in Europe, the services developed by the European Space Agency and the European Commission as in the framework of the global monitoring of the environment and security are being developed by the private sector. So that is instrumental in bringing to fruition the knowledge in terms of data analysis and algorithms, in terms of actual information that is usable in practice. Then, and with high resolution information products, the situation is different. What you see is the development of services that work upon subscription. So, and the advantage is to provide competitive information to farmers, a competitive edge in the sector. So that's naturally as a commercial development in the future, because it would not make sense to have that type of information. The public domain would lose the value, basically.
Okay, thank you. And I'll try one more question, which is many of the satellites that we've discussed today are large international cooperations. And the question here is, do you see the increasing capabilities of CubeSat as the start of a paradigm shift that will move away from these large spacecraft to these smaller, more affordable ones in order to do the crop, water, and weather monitoring?
I think this is a good concept for the small satellites. As I take Chinese satellite examples. Chinese launched a few years ago 2 small satellites. We call them HGA satellites, and they provide CCTV data with swarms of 800 kilometers. And every 2 days have one we can cover the whole China. So we use this data to monitor crops. So during the crop season, we can have 6 or 7 different days of soil data. So it's make it more easy for us to monitor crops instead of before. We can fully coverage everywhere in China and do more precise. So I think small satellite is a very good concept for the future.
Okay, we have so far many Earth observation satellites on space, and I don't think the small satellite is not the only answer, because more international cooperation or data exchange should be emphasized. And I want to identify the another issues concerning Earth observation data. That is orbit selection. In other words, local sun time. Many satellites flew on 10:30 or 1:30 p.m. So, and some radar satellites flew only dawn satellite 6 a.m. and 6 p.m. So, actually, we don't have data except such specific local sun time. So far, we cannot get the data in 3 p.m. or 9 a.m. or 8 p.m. and so on. So the observation interval is very essential to estimate the ground phenomena precisely. We need more different orbit.
I would take this argument about orbit selection in a different direction. In the sense that if you combine that with the trend in the direction of smaller and cheaper satellites, and also the fact for many applications like assessing crop conditions, you use relatively simple measurements, and so that adds up to a rather simple mission that has one requirement: has to acquire data reliably, frequently, at high spatial resolution. That essentially means an orbit designed to tailor the observation needs of a specific area and neglecting global coverage. And now, if you figure out the cost of very small satellites with a simple multispectral imaging radiometer doing the type of observations, then you will quickly find out that the cost is perfectly consistent with the amount of resources that are involved into the management of agricultural production or monitoring the climate in a city. You could years ago I did a study with a group of students about how much it would cost to construct and launch a satellite to get high-resolution thermal infrared data of Rotterdam, which is a city near there. And then we ended up with a surprising figure that if every inhabitant of Rotterdam would be prepared to pay $8 per year, then they would get a satellite and to get the data. Something like this, people may just do for the curiosity of having updated information about their environment. And, so it is a technical possibility that should not be neglected.
Okay. One of the important things, of course, is that we have a near real-time data stream coming down, especially if we're following the water. And we need to know what's happening across the globe. We need to know rapidly. So that's another element that we haven't really gotten into. We don't have time. I'd like to ask one more question, and that is, we have talked a lot about drought. And do you feel that the frequency of drought is increasing around the country?
Yes, I think so, especially in China, where the frequency of drought has increased. This, I think, is the result of both natural climate change and human activities. In the neighborhood of Beijing, 40 years ago, it's full of wetlands in Beijing, and we are suffering flooding almost everywhere. And in 1965, we have a historical flood in Beijing. Then, government starting to prevent. They are digging a lot of canals to bring water directly to the sea, and then they plant the trees and the reservoirs and the other streams. So now we are suffering from the drought.
What you see both from current data and also like the regional climate scenario is changes in the distribution of precipitation, and which is a factor enhancing the risk of an increasingly high frequency of drought. And I think then the combination with, for example, development of irrigation water management then becomes another type of reasoning, and it's not so much a natural process anymore. That is is a decision or the way water resources are allocated that could change the incidence of drought in specific areas.
Well, I think that's all the time we have. We've overrun our 1 hour allotment. I would like to thank first the staff, the IAF staff that has handled the logistics for this. It's been excellent and fielding the questions. Thank you. I'd like to thank the audience for getting up early in the morning here after probably going to several receptions last night. We do appreciate that. And most of all, I'd like to thank the 3 speakers that have come, some from as far as 500 meters and some from the other side of the earth to come and participate in this. So thank you all. The speakers will stay up here if you have any questions.